Good morning, everyone. Today we'll continue on recurrence relations to discuss how to solve recurrence relations. All right, so let's continue with this example. We have n circles on the plane, and we want to find out the maximum number of regions divided by these n circles. Of course, if we have one circle, there are two regions. One circle, one region inside, one region outside. All right. So for two circles, there will be six. There will be four, and for three circles, there will be 8 regions. So that's the maximum number. So here are 3 circles. So divide the plane into 8 different regions. All right. So from this initial condition, so the small value of n, we will see that it seems n Rn number of regions, it seems to be a power of 2. So for 1, 2, 3, it happens to be power of 2. All right. One way to find out the maximum number of regions is to obtain a recurrence relation for Rn first. So we can easily obtain the following recurrence. Rn equals, if n equal 1, there are 2 regions. All right. Now, for R equal n, without this circle, there will be Rn minus 1 different regions. So divided by n minus 1 circles. Now with 1 circle, if this circle, if I add a new circle, if this circle intersects with an older circle, then this circle will be divided into 2. So it will create one more region for each older circle. So therefore, here will be plus 2n minus 1. So that's the maximum number. All right, so that's n at least 2. So get this recurrence relation for R of n. As we discussed last week, we can use iteration methods to find this one. Recall one thing I mentioned, it's important not to simplify it when we use the iteration method. Otherwise, we may not be able to find a correct pattern. So for example, for this one, if we use iteration method, all right, now if we simplify that, that gives us 4. That's for this one, 2 from. Okay. All right, then R3 equal R2 plus 2 times 2, so 2 times 2, 4. So our first 3 value will see that Rn equal to power n. So that's why I said if we guess the solution, so if we guess this one, then it's very important. We need to prove it. Normally use mathematical induction. So in case this one is not correct answer, we may be able to find it when we use mathematical induction to prove it. So for this particular one, if we use mathematical induction to prove it, we'll see what the induction will not go through. All right. So suppose it's old. First induction hypothesis. Now, when we consider Rn, so use the consideration, we get Rn minus 1 plus 2n minus 1. Now using induction hypothesis, what we have here is this one, 2n plus 2n minus 1. So that's what we want to get. But certainly this one cannot equals 2n. So we see this one cannot be correct answer when we add it to use induction to prove it. So that's the importance of using mathematical induction when we guess a solution. If we guess a solution, when we get a solution, it's very important. We need to prove it using mathematical induction. If we are not, if the induction is not guessed, but rather we obtain it using a sequence of arguments, then there is no need for mathematical induction. In this case, we make an educated guess, looking at the pattern. It looks like 2 to the power n, so make educated guess. But then when we try to prove it, we'll see this one actually does not work. All right. So that demonstrates the importance of using mathematical induction to prove our guessed solution. In this case, if we follow my suggestion that do not think of that, then we'll be able to obtain the correct answer. Okay, so let's see. It's often useful to organize steps in equation from starting from Rn instead of from R1. All right, as we discussed last week. So that's what we get if I did not make mistakes. So it's up to R1 2 times 1. So just here the n minus 1, so 2, 1. Here this part is saying that this one, so 1 times this one. Now we add them up. These things crosses each other. So then what we get is, so this one equal 2. All right. So that's what we get. We have closed formula of this one. So that's very easy, the summation. Typically, when we almost always when we use iteration method, eventually we need to deal with summation of some terms. It's not easy at all, but for some simple ones, we know how to obtain simple formula. Close the formula. For this one, it's 2n times n minus 1 divided by 2 plus this one. So eventually, that's give us solution n squared minus n plus 2. The correct answer is this one instead of it's not this one. So this one is wrong. Rather, this is the correct answer. All right. So this example illustrates the importance of not simplifying the term value. Simplify the terms when we extend it. So keep them in that form. Then we see the pattern. So eventually we deal with summation of this one. All right. Okay. Now one more example before we get into general results. All right, let's look at this recurrence relation. For the number of comparisons, we use to find both minimum and maximum integers from n integers. Using divide and conquer method, we divide into two parts. Find the minimum maximum from both sides. Then find the minimum between the two minimum elements, maximum between the two maximum elements. So that's number of comparisons. Two elements are called from comparison. Otherwise, there are two here. Okay. Otherwise, two parts here. I half of n elements, so half of n twice plus this one plus two more comparisons. All right. Now here the difference is the previous recurrence. We see the recurrence of an based on an minus one something or perhaps n minus some an minus two or something. But here this one is not n minus something, but n divided by two. All right. So for symplectically, let's assume that n is power 2. So that's each time that will be even. Otherwise, it's a little bit more complicated. And later on, next week, we'll discuss it when we discuss asymptotic notation. All right. But for time being, let's assume n is power 2. So that will ensure each time both will be still power 2. So it's evenly divided. Okay. So one way to deal with this type of recurrence actually is to transform it into a different recurrence. Because here n is power 2. So what we do is define a new function, maybe k. Instead of based on n, g is based on k. All right, g is based on k. So now for this one, from here we get reference for gk. When n equal 2, k equal 1. So here k equal 1. Its value is still same, this value. Now reference this one. Instead of Cn over 2, here g k minus 1. So that's a new recurrence. In order to solve this recurrence, what we need to do is solve this recurrence, then transform it back to C of n. So once we have gk, then we have Cn, C of n. All right. Just replace k by log n. So that's what we obtain. Okay, it's k equal log n. So here the relation is k equal log n. So instead of based on n, now it's based on k. Now you see the recurrence is a linear combination of previous term is gk minus 1. Okay, so let's see. Do I need to give the full ones? Okay, I think I will skip the details. It's same, basically same. Just give you the final formula. Okay. So for this one, eventually we'll obtain. Use the same idea. We can list. So gk equal 2gk minus 1 plus 2, 2gk plus 1 equal 2 squared, gk minus 2 plus 2 squared, and so on. All right. So eventually we get gk equal, let's see, it's 2k minus 1. Let's see. Let me, to make things easier, let me just copy it. 2k minus 1. This is 2k minus 1 plus. It's a summation part will be 2k. Here, another minus 2, I think, eventually. Set the value what we get. So here, summation part, this first term. Okay, I ignore details. All right, just simple manipulation of these things coming out. Eventually, that's what we get. All right. Now, once we get this gk, we can obtain. We can simplify this one, or we can just replace it. But if we simplify this one, is say 2k minus 1 here times 3 minus 2. Okay. Now this one can be replaced. Now in order to get a Cn internal n, this one equal n over 2. So here's Cn minus 2. Eventually we obtain this one as solution of Cn. So that's the number of comparisons. Because when we discuss induction, we try to prove Cn at most 3n over 2. So actually exact value is 3n over 2 minus 2. All right. Okay. Here it illustrates that by transform, use a different representation of this one, or transform this one for different recurrence relation. So we can solve this recurrence relation and get back to this one. It may be easier for this type of recurrence relation. So instead of n over 2, here is k minus 1. So that's what illustrates this idea. All right. So here we discuss a few examples where we can use iteration method to solve some recurrences. Unfortunately, typically it's very difficult to obtain closure formulas for recurrence relation in general. It's very, very difficult. So here just we're lucky that we will be able to obtain some, because eventually we need to deal with summations, because summation is not easy at all. For example, even for very simple ones. So summation of 1 plus 1 over 2 plus 1 over 3 plus say 1 over n. This summation. No one knows the closure formula. So I think practically it's very close to log n. Okay. So even for polynomials, 1 plus 2 squared, 3 squared, it's not easy as well. Okay. All right. Sorry, let me check the cell phone. I ignored some of your charts. Is there anything? Okay. Okay. Let me turn off my phone. Sometimes phone coming in. General office. Some from the department. Okay. Right. Okay. Luckily, for some form of request that often very often in practice, we do have a general way to solve it. One important type of recurrence is linear recurrence. One type of recurrence relation is a linear recurrence with constant coefficients, like the Fibonacci number. This type of recurrence. So it's a linear combination of previous terms. And the coefficient here will be constant. So here maybe 3, here maybe 5. Here and -2 and -4. This type of translation, we have to have a general a way to solve it. In other words, we do have formulas for solving this type of recurrence relations. Okay, the method for this kind of thing is quite mechanical. Actually, it's much more like high school mathematics. So the following one or two lectures will be very similar to high school things. It's just basically I give you formulas, just as solving quadratic equations, this type of thing. So it's simple. Once I tell you, it's quite simple. It's tedious and mechanical. You have to be careful when you use it. All right. So the idea, the whole thing is really kind of straightforward. Okay. So let's discuss them. Let me start with the first order, the translation, to give you a feeling first. It's also called the linear difference equation, linear difference equation. So instead of this one, it's also called the linear differential equation. Actually, the idea is very similar to solving differential equations. If you're familiar with that from calculus, then it's very straightforward. Otherwise, it may seem to be not that easy. Otherwise, it's very straightforward if you're familiar with how to solve differential equations. Okay, so let me start with a very simple one. So let's consider this type of recurrence rate. Very simple one. We have solved a few of them already. Use the iteration method. Okay. So here we assume that first order, then this one A is not zero. Both A, B are constant, say real numbers. We encounter this kind of recurrence relation very often in practice. So therefore, it's good that we try to solve it in general. Then when we have a new relation, we can just use same method. Okay. So let's see the example, the Tower of Hanoi, problem. Okay, or I can give you another one. So here equal 2, here maybe 3 and 3s and minus 1. Let's see one example again, minus 1. So that's linear reconciliation. A boundary condition, we only need one value. Boundary condition needed one value. Typically, it's maybe S0. That would be good enough. All right. So for this type of reconciliation, it's quite easy to solve it using iteration method. We can just use the method and then to get a formula for this one. So extend a few terms to see what's going on. Okay. All right. So eventually we get to. So here will be the boundary condition. So will be A S0 will be here. All right. So here will be A to power n plus A n minus 1b. So be careful with these. The only thing you need to be careful is here, the exponential part. All right. So let me check if I made. I very often I made typo for these mechanical things. I'm not good at these things anymore. Okay. I'm too old. Okay. At your age, of course, it's quite okay. Let's see. So this is using cancels. So eventually, what we need to deal with is summation. So you see, first is the exponential function of A. So if we ignore this part, it's easier to see if we just exponential function of A, if without this part. Okay. So this part contributes to this things. So then this part is summation of B 1 plus A plus A to power n minus 1. The solution to this one, Sn is this one. We need a closed formula. So what we need is a closed formula for this one. This is easy. All right. This one. Now, only thing you need to be careful is this summation depends about value of A. If A equal 1, so this one will be NB. when A equal 1. So from here is A to, I can rewrite it as A0. So 0, 1 to n minus 1, n terms. Right? So here will be this one, when A equal 1. When A is not equal 1, let's see. Normally, maybe I should write A n minus 1. A not equal 1. So this summation on the geometric sequence, everyone knows what is this relation. So that's what we get. All right. So we can reorganize this one a little bit. Yeah, maybe write as A. Okay. So that's the solution for this one. If the solution depends on whether A equals 1 or not. If A equals 1, this part is NP. Otherwise, so first one thing is this one, just rewrite it. If you want to remember it, maybe this one is a little bit easier to remember. Actually, I don't recommend you to remember this formula. Rather, you should remember the idea. It's a method to obtain it. Then you will be able to obtain this one by yourself. It's not, even if you remember it, it's easy to make mistakes. Here is plus 1 or minus 1, here is plus 1 or minus, and it's a plus or minus. It's easy to forget. Out of C, what the value of C, it's easy to forget. So I really do not recommend you to try to remember this one. So rather, I would rather use that remember idea to obtain this one. So then you can reproduce yourself. Of course, you are very young, so it's easy for you to remember this. For me, it's no way. Okay, tomorrow I will forget. Okay, I'm too old. But for you, you can remember it. Let me check if it's correct. Okay, I think it's correct. I did not have a typo here. All right. So that's the general formula for this one. All right. So with this one in hand, then if you're lazy, then for linear recurrence, we can just use that formula. It's very simple. So it's just very tedious. It's not interesting at all. You just apply this one. Not fun at all. Okay. You may have this kind of problem in exams. But to be honest, it's not fun at all when we can use formula. Just straightforward things. All right. So let's see. Let's try to use this one to solve one recurrence relation. Uh, let's see. Okay, so let me give you an example. This is a really very practical example. Let's see, where do I have it? Oh, yeah, yeah. Debt repayment. All right. Suppose we borrow this $0. We borrow this with interest rate, monthly interest rate. So here, say suppose we monthly interest rate. Oh, that's how is monthly interest rate. Okay, so every month we pay the P. Monthly payment say is the P dollars. So we want to know the balance of n months. The Dn balance of n months. Well, that's a very, very practical problem. When we have mortgage for your flat, maybe or credit cards, monthly installment. So basically, it's based on this one. And normally, we just trust the bank. Whatever they do, we just pay them. Okay, whatever they say. But how do we compute this one? Actually, sometimes banks make mistakes. So don't trust them 100%. Right? So it's better to know that how this one is computed. So then we know what's going on. All right. So for this one, we can have a difference relation. So cost again. Initially, DCL, that's our balance. All right. So after n months, what happens? Interest is computed based on the balance of last month. The interest, this interest, this is the original amount, the n minus. This is the balance. N months without this pay, without this monthly pay. Now we pay by T, so it's this month we pay the $T. So that's the balance of n months. We get a recurrence relation for this. All right. So here n. So the debt repayment of this part of the monthly payment is $T, and the balance of n months are basis following the recurrence relation. This is a linear recurrence relation where A, if we match this one is A. This one is B. All right. So we can use this formula directly. Here, A is not equal 1. If A equal 1, you're very, very lucky. So you pay no interest at all. Okay. Only in your dream. Okay. Only in your dreams. This R will definitely more than zero. Okay. So we apply this case. All right. So you can see actually the thing really grows exponentially with interest. All right. So if we just use this formula, you can easily get dn equals. It's really grow exponentially with this one. So really interest is really a killer. All right. So initial value is D0. So C is this one. Okay. A minus 1, so it's R minus T. B is my, oh, it's T again. Okay, so C is. So it's here to be plus, I think. Okay, so there's a formula. The bank computes your balance after n months. You see that it's very, very important. Interest rate is really a killer. So whenever you negotiate with the bank, you should really aim for this one. If you're able to get this one lower, then it's much better for you. All right. Okay. So this is a straightforward form application of this formula to solve this reconciliation. Now, in practice, sometimes this one, for this initial value may not start with S0. So sometimes we start with this S0, but usually it's not. Maybe it starts with SK for some K. So in general, it can start with some K instead of this one. Then that formula will be shifted by K positions. So if I remember correctly, it will be, so then the answer will be something like this. So the translation will be still same. So initial value is SK instead of SCL. when n equals k. We have this one. Then the solution will be shifted by k positions. So initially we have S0, S1, S2, S3. Maybe here is SK. Let's see SK here. Now what we can do is construct another recurrence for another sequence. So say T starts with K. All right. Now for this one, we can use this formula to obtain solution for this one first. Then transform it into solution for SK. So in other words, this position is shifted by K places. Let me just give you the formula for this one. So it's quite simple. We just shift it by K positions. So then answer will be SK, Sn is still same here. So it will be shifted by K positions. Instead of n, so here will be n minus k. All right. Now here xk plus c minus c. So here will be also shifted by n minus k b positions. Okay, so here is a not equal 1, k a equal 1. C is same, okay. C is same as this one. C is still same. So again, I don't recommend you to remember this formula. Rather remember the idea. What you can do is from S, you construct a new sequence T, then use this one, then shift by K positions. But really be very, very careful. It's very easy to make a mistake here. When you remember the idea, but you, as I said, it's very, very mechanical. It's tedious. It's very easy to make mistake here. So whether it should be n minus k or n minus k minus 1 or n minus k plus 1. Here n minus k exactly, or it's easy to make mistakes. Sometimes it can be deferred just by 1. So really be careful. Instead of try to remember these formulas, rather I really suggest remember the method. But try to obtain these formulas by yourself. Even you forget, then you will be able to get these formulas by yourself. All right. Otherwise, if you don't know the method, just remember the formula, then you will be there's no way to tell whether here should be minus c or plus c, or where should be minus c or plus c. It's easy to forget. All right. Okay. So that's what we know about linear first order linear reconciliation. This will give us, and this will give us a feeling what solution looks like. Basically, it's an exponential function. So we need something much more than just the first order. Okay. So in general, we need to deal with reference based on more than one previous terms, like Fibonacci number. So let's first consider this type of reconciliation. So the summation, there's a term Sn together two previous terms. We don't have other terms. We don't have things like plus b plus n. We don't have these things. So all these terms are previous terms. So then it's called homogeneous. So first, let's consider homogeneous second order reconciliation, linear reconciliation. So we have this form, all right? Suppose let b not equal to 0, a can be 0, a be real numbers. So let's count this type of reconciliation. One typical example is Fibonacci number. So here both A and B equal 1. What we would like to know to obtain a closed formula, for example, especially for people that number, because this number is so important, it would be nice to obtain a closed formula for this one, right? Okay. Now, how can we solve this type of translation instead of the first order? Now we deal with second order. Of course, the first reaction, maybe we try the iteration method. We can try to use same method. But very quickly we find it's almost no way. So suppose we do this, okay, try iteration method. So then here we will list fn minus 1 equal fn minus 2 plus fn minus. So this time will be here n. So this one, these two terms, because these two terms, we need two of them in order to cancel it. So then these will cancel. All right, now we need to deal with this one. Now you see the difficulty here. Here 3. All right, now here we have 3 terms, n minus 2, n minus 3, n minus 4. So here we will need to write this one here. So we need to write n minus 2 here, 2n minus f n minus 3, here 1 f n minus 4, and so on. You will see it's getting much more complicated, more and more complicated. It's almost no way to discover a pattern from this method. Okay. So luckily, we do know how to solve this type of translation. So it's really based on an equation. So for this recurrent, we have an equation associated with this one, and root of this equation actually tells us what the solution looks like. So for this one, there is the translation. For this is the translation. So based on our experience, we know this solution typically will be of the form Rn. So something like this. Solution will be of this form. Okay. Now, in order for this one to be a solution, so if we plug it in, what happens is we'll have, so this R will have to satisfy the following relation. If indeed the solution has this form, and I don't mean exact solution, but if it's of this form, so maybe C times something, it must satisfy this equation, right? Now we cancel, if we cancel this one, R n minus 2 from both sides, so what we get is Rn 2 equal AR plus B. So that means R must be a root. R must be root of this equation. All right. So this equation is called characteristic equation. All right. So then the solution will be related to root of this characteristic equation. So what we do is we first need to find the root of this characteristic equation, then obtain the solution of this one. Remember, this is a quadratic function. It may have two roots. It always has two roots. It can have two identical roots or two different roots. So we will have two roots, R1 and R2. Then the solution of this one depends on whether these two roots are identical or not. The solution of this one is okay. So it's a linear combination of these two, if these two roots are different. Otherwise, if these two roots are same, then the root raised to power n but then multiplied by a linear function of alpha and beta, of n, alpha n plus beta. And these two values, alpha beta, will be determined from initial conditions. So we'll continue after break. Okay, so let's have a break first. Yeah.